My name is Muhammad Tarq bin Mahmoud, matrix ID 24822, and today I'm going to show you how to solve the questions that were given in the assignment. Things first, question 1 gave us this diagram and they asked us to determine the reactions at the supports and also to draw the shear force and bending moment diagrams. The question also gave us that B is a roller and that EI is constant. So first things first, we have to do the principle of superposition with the formula R equals to 3n. So R is actually the number of unknown reactions within the structure, and also that n is the number of parts that were involved. So seeing as this is a fixed n and this is a roller, we have 4 forces: By, Ax, Ay and Ma. So altogether we have 4, and since this is near a beam, there's one member. So from here we can see that the number of unknowns are greater than the value here. So it is statistically indeterminate by the first degree. Okay, now that we've found out that, we have to go to the compatibility equation. The general formula that was given was 0 equals to negative delta B plus By FBB. But these negative and positives are actually sign conventions that depend on the question, which depend on these 3 drawings that we have. So the reason why we got negative delta B is because when we check this diagram here, due to the UDL that was placed on top, it shows the structure deflected downwards. That means below its original height. So we take that as that is negative. And for here, after we add the virtual loading 1, it shows that the structure is deflected upwards, showing the positive. Okay, so we get these full equation. Now to find these equations, we actually use a formula, integrate of mm over ei dx, and also small m ei dx. But since this is a beam, there was already a table given to us, and we simply just take the equation needed and just fill in the equation, substitute into the equations back. So we get negative WL4 over 8EI and negative L3 over 3EI. So next we just shift the formulas, and eventually we'll get By equals to 3 over 8 WL. Okay, so next, the final part, we have to use the equation of equilibrium. The equation of equilibrium, there are 3. That is the Fy, the Fx and the moment. So depending on the question, we can choose either to do moment first or moment Fy first. So I chose to do moment Fy since we already have By 3 over 8 WL. So substitute all the equations that we have, all the values that we had. Eventually we will get Ay equals to 5 over 8 WL. And then next, for moment, I chose moment at B. So referring to the graph here, we substitute everything into the equation, and we will get Ma equals to WL square over 8. So this is basically how we determine the supports. It's the support reactions, the reaction for the supports. Now the other question asks us to find the shear force diagram and the bending moment diagram. So before we start drawing the diagrams, we have to find out the equations for shear force and moment, bending moment. We can do this by cutting the structure anywhere in the middle, and then ending up with this summation of forces. See, this is how we get the V, this is how we get the M, N, and we substitute any other values that we previously had. So first, to find shear force value, we use the summation of Fy. Force of Fy equals to 0, and then we will get this equation. V equals to 5 over 8 WL minus Wx. And for bending moment, I choose a moment at where I cut originally here. So M equals to 0. After I substitute all the values from the previous equations here, eventually I get this one new equation. So for V and M. So before we start drawing here, we have to identify where will it be marked on the graph depending on the x. So for V, when x equals to 0, so x 0 we substitute inside the previous equation, and then we get 5 over 8 WL, means it is marked up here. And then next point we choose is x equals to L. So if we substitute L inside this value, after we subtract 5 over 8 WL minus WL, we will get negative 3 over 8 WL. And we get this point here. And we just draw to this point, and this is how we get the shear force. Now the bending moment diagram is the same thing. Using the equation that we got, we substitute x equals to 0, we will get negative WL squared over 8 down here. And x and L, M will equals to 0. Eventually everything will subtract and it will become 0. But this is a bending moment diagram. So as we can see here, we will need one more factor, that is to find the max moment. At max moment, V equals to 0. So to find the x that is involved, V equals to 0, and then we get this short equation where x equals to 5 over 8L. Now this 5 over 8L, we substitute inside this M equation, and then we will get the value of M, the highest max moment here. And that is how we draw the shear force diagram and the bending moment diagram. Okay, so now we have solved everything for question 1. Later I will move on to question 2. Okay, moving on to the second question. Okay, so the question gave us this structure, and they asked us to determine the reaction at support. They also told us that AC, A and C are pins, B is a fixed end, and EI is constant. Okay, so first thing first, like usual, we have to identify the principle of superposition, R equals to 3N. So because this is a frame, we are going to have to cut at some points. We have to cut the diagram at 2 places, mainly here and here. So we end up with 3 parts, as shown as I've drawn here. So from here, we identified that there are this many forces. They have 2 forces at A. There are actually 3 forces here, because this is a counterbalance, the equation of equilibrium. So there's only 3 forces here, another 3 forces here, and 2 forces at C. And that's how we were able to get altogether 10 unknown reactions. And referring to the number of parts that were involved in this, there are 3, because we have 1, 2, and 3. So that's how we get 3. So in the end, we actually found out that it's statistically indeterminate by the first degree, more by 1. Next, we had to go with the compatibility equation. So same thing, compatibility equation, 0 equals to delta C plus Cy FCC. So when we draw out the mark, here are the pins, and shows the bend we get because of the UDL equals to, and then we get the forces here, delta C. When we replace the pin here with roller, we notice that it started moving. We can see that it's already shifted in movement. Same with here, and that's how we get positive delta C and positive Cy FCC. Okay, so from here based on the diagram that we've drawn previously, we find the moment at A first. So after substituting all the values, eventually we end up with Cy equals to 202.5 kilonewton, and then we find summation of Fy equals to 0. So after substituting everything, we get Ay equals to 157.5 kilonewton. And since this is a pin and there is a force acting in the horizontal action, we will also need to find Fx. So Ax minus 33 equals to 0, and Ax we will get 90 kilonewton. Okay, so next we will have to identify the equations that we need for both the delta C and the CSFCC. We will need to redraw this to find the M's, the big M's that is needed into the formula. So after we put in the new values, we will get 2 new equations. M1 equals to 0. We will get 157.5x minus 30x squared, and M2 equals to negative 15x squared. Alright, next we need to find the support reaction at the virtual, similar to the previous one that we've drawn. Instead, we have to show where we applied our virtual loading. In my case, I put virtual loading at Cx. So to find the same process as before, the moment we shift and then we get Cy equals to 1 over 2 kilonewton. With the summation of Fy, Ay we get negative 1 over 2 kilonewton. The negative just indicates the direction. So, and Ax we get equals to 1. So, we get to find the M1 after resubstituting the values that we've got initially into the same diagram. We were able to get the M1 equals to negative 0.5x and M2 equals to negative x. Okay, now to identify the delta x and the FCC, we have to use the integration formula. Mm equals to over Ai dx and small mm over Ei dx. So after we substitute all the values that we previously had before this into this long elaborate equation, we end up with this. See, this equation. Continuing with our equation just now. Now we are finding FCC, which is our virtual. Just now was applied. So with virtual load, we same thing. We substitute the new M1 and M2 that we've had into the integration formula, and eventually we will get these new values. Now these values that we get for applied loading and virtual load, we are going to substitute it right back inside the equation that we initially had. And because of this, after shifting the formula, we will end up getting our redundant force is 18.75 kilonewton. Now, finally, to find this total supports that we've had before this, we'll use the Cx value is going to be substituted back into the structure that we've initially had, and proceeded with the equation of equilibrium, where we have to find the moment, the Fy, and the Fx. So after substituting all the values that we need, we found that Cy, the new value for Cy is 211.875 kilonewton. So this value is going to be reused again in Ay to find the Fy during the substitution of Fy equals to 0. So Ay equals to 360, as you can see at the top here, minus 211.875. We will get that Ay equals to 148.125 kilonewton. And finally, Fx equals to 0. We will use Ax minus Cx minus 30 times 3 because it's UDL. So we get, since we already have the value of Cx, so it's going to be 18.75 plus 90, and then we get the value of Ax equals to 108.75 kilonewton. So basically that's everything we have to do. We have already answered the question, which is to determine the support, the reactions at the supports. So hopefully you understand and were able to follow my question. Thank you for watching. And to repeat myself, my name is Muhammad Tarq bin Makmur with matrix ID number 24822. Thank you.